Hello, this is Richard Hammack's Calculus 1 course. We are in part 3 of the course on derivatives. Today, lecture 22, higher derivatives. The idea of higher derivatives is simple. If we have a function, say f of x equals x to the fourth plus x cubed plus x squared plus 1, we can take its derivative with familiar rules. F prime of x is 4x cubed plus 3x squared plus 2x. And this derivative, like f, is a function. In fact, it's a polynomial. So we can take its derivative. The derivative of f prime of x would be denoted f prime prime of x. And again, with familiar rules, it's 12x squared plus 6x plus 2. This f prime prime, which is the derivative of f, is called the second derivative of f. And of course, there's no reason to stop with the second derivative. We could take the derivative of the second derivative. That would be the derivative of f prime prime, which we'll denote as f prime 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 of x. And that's the derivative of 12x squared plus 6x plus 2, so it's 24x plus 6. And that's called the third derivative. And of course, you can keep going. You can take a fourth derivative, which would be the derivative of the third derivative. There's a shift of notation here because you can imagine you're going to get tired of writing lots of primes for your function f. So at the fourth derivative, that's denoted not f with 4 primes, but f with the 4 in parentheses superscripted. And it's the derivative of your third derivative, so it's just the constant function 24. So we say the fourth derivative of our function f is 24. The fifth derivative would be the derivative of 24, which is 0. And the sixth derivative would be the derivative of the fifth derivative, which is also 0. So this process obviously could continue forever. And after the fifth derivative, you just get 0 for this particular function f. So that's today's topic. Higher derivatives mean derivatives of derivatives. Given a function f, we can take its derivative, which we sometimes call the first derivative, and then continue taking derivatives. That's what a higher derivative is, a derivative of a derivative. You can see in our first example, we started with a function which was a polynomial, and by continually taking derivatives, we boiled it down to 0. Got it to be something incredibly simple. That needn't be the case. Sometimes with some functions, they get more complicated as you take their derivatives. For example, think of f of x equals x to the minus 1, which is 1 over x. Its derivative, f prime of x, by the power rule is negative x to the power of minus 2, or minus 1 over x squared. If we take its second derivative, that's the derivative of minus x to the minus 2, again by the power rule, we get 2x to the power of minus 3, or 2 over x cubed. The third derivative would be the derivative of this. That works out to be, with the power rule and the constant multiple rule, negative 6x to the minus 4, which is minus 6 over x to the fourth. The fourth derivative, again by the power rule, is 24x to the power of minus 5. The fifth derivative, again by the power rule, would be negative 120x to the power of minus 6, and so on. Here's the sixth derivative. And you can see here that for this function, the derivatives are, in a sense, getting worse and worse, more and more complicated. The powers increase rather than decrease as they did in our first example. Here's another example. Think of the function y equals sine of x, and take its derivative y prime, which is cosine of x. Its second derivative could be denoted as y prime prime, that's the derivative of cosine of x, which is minus sine of x. The third derivative, y triple prime, would be the derivative of minus sine of x, which is, by familiar rules, negative cosine of x. And now let's go to the fourth derivative, which we would denote this way. It's the derivative of minus cosine of x, which is minus sine of x, or just plain sine of x. So look at this. When we got to the fourth derivative, we got back to our original function sine of x. The fourth derivative of sine of x is sine of x. And so you can see for here ever after, as you take higher derivatives, that pattern's going to continue. Sine, cosine, minus cosine, back to sine. Forever. So here is a function, sine of x, that gets neither simpler nor more complicated as you take its derivatives. The higher derivatives give you a cyclic pattern of period 4. Let's talk about notation. If y is equal to f of x, then we know that f prime of x is also denoted as y prime, or sometimes d dx of f of x, which you could also write as d dx of y. Also as dy dx. Think about how this notation would continue with second derivatives. F prime prime of x would be denoted y prime prime, and that's also the derivative of d dx of f of x. So d dx of f of x. What we're going to do is denote this ddx times ddx that you see here, not really times, they're operators, but this ddx paired with another ddx as d squared dx squared. That stands for two of these derivatives here. So you might denote this second derivative as d squared dx squared of f of x. And that f of x is y, so continuing this notation, that would be d squared y of dx squared. So the point I'm making is that this notation here is our notation for the second derivative of y equals f of x. The first derivative is dy dx. The second derivative is d squared y dx squared. So notice that this 2 appears in the superscript of 2 appears in different places in the notation. And that's just the way the notation runs. You can see that it comes from something commonsensical here. And you want to get used to it. It's just it's nothing deep here, it's just notation. For the third derivative, f triple prime of x would be y triple prime. That would be d dx of what we had above, d dx of d dx of d dx of f of x, which is streamlined as d cubed over dx cubed of f of x. And changing that f of x to a y, that's d cubed y dx cubed. And this notation continues. The fourth derivative would be the fourth derivative of y, or if you prefer, which you probably don't, but you could certainly write it as d dx of d dx of d dx of f of x, or d to the fourth over dx to the fourth of f of x, and changing that f of x to a y, we get d4y dx to the fourth. So that's our notation for the fourth derivative. Now, as we continue in this class, higher derivatives will begin to play a special role in many applications, and you're going to see this notation in action. So when you see d4y dx4, you'll know that's the fourth derivative. And obviously this continues in the obvious pattern. The fifth derivative would be denoted d5y dx5, and so on. So a few examples. if y is equal to x cubed, the derivative dy dx is 3x squared. The second derivative would be denoted this way. D squared y dx squared, that's the function 6x. And the third derivative, d cubed y dx cubed, is 6, and so on. You'll need to keep track of variables here. If z is cosine t, the first derivative is dz dt, which is minus sine t. The second derivative would be d squared z dt squared, which is minus cosine t. The third derivative is d cubed z dt cubed, which is sine of t. So on this page is the notation that we'll be using. Again, it's nothing deep about the notation. It's just notation. It's the way we express things mathematically. The big idea is we have what are called higher derivatives, derivatives of derivatives. You should get some practice with this. It's good practice for the rules of differentiation, and it's also good practice to begin to wrap your head around the notation that we've talked about. But that's it for today. You'll see more higher derivatives as the course continues. But our more pressing concern for now is what's coming up next. In the next lecture, we're going to introduce a new rule called the chain rule, and it's a rule for the derivative of the composition of two functions, not the product of two functions, but the composition. And this is going to be a big rule, so stay tuned for this. We'll work this out, and we'll spend some time working on some more derivative rules, and eventually we'll talk more about applications of derivatives and meanings of derivatives, and mixed in with all of this will be higher derivatives as well. So next time, chain rule. I hope to see you then. Goodbye.